Hi, my name is Arkajit Dey, and I'm from the Marketplace Locations team. And today I'm here to tell you a little bit about how we process locations in our system. So specifically, I'll kind of talk about the kind of indexing, serving, and storage systems that we built at Uber to process all the location points that, that our entire system is inputting. So just to give you an idea of what I mean by location point, you can think of it as a latitude and longitude, and I'll go into more detail in my talk. But before I get into nitty gritty, I just want to first orient ourselves by looking at like a sample trip and just go through what happens during a trip to motivate why we need these systems. So let's start there. Cool. Yeah, so when you first open the app, you probably see a screen that looks something like this, right? You've probably seen it hundreds of times. And you may not even like, you may just be like, going through without paying attention because you're just so used to it. But today I just want to call out some features of this screen. So the very first thing you might notice when you open the app, well, there are cars around. There are a lot of cars. There are all the available cars just kind of moving around in the app. And this is one of the coolest features about Uber, the one that makes you feel that Uber is alive, the city is buzzing, and like people are there waiting to take you somewhere. So that's one thing that the app kind of shows you right away. And then another couple small details I want to point out is you'll notice that the cars are actually on roads. Now, this might seem like kind of a obvious point, like, well, they're not flying, right? Well, not yet, but we might get there one day. But yeah, the cars are actually on roads. So this small detail is also something when we track our location data, we have to know like which roads the cars are on. And additionally, we have to know like where they're going, right? So like I pointed out, there's a red car and a green car. They're going in different directions, and that actually matters, right? So one example for why that matters is a car going the wrong way on the street like might not be able to pick you up in time. So that might be the difference between a 2 and a 5 minute ETA. So getting those small details right is also important. Cool. So this is where your Uber experience probably starts. From there, if you like what you see, you probably click the request button. And so what happens then? So you probably see a screen like this, like Uber is doing something in the background, some magic is happening, right? So what's going on here? So today I want to tell you a little bit about that, right? So you can think that at a high level, what we're doing is we're trying to figure out what's the best car to send to you for your trip. And how are we going to do that? So one of the systems I'll describe today is like a system for basically storing all the car locations so we can quickly index them to answer these kind of queries. So you can imagine that we'll need some system that knows where all the cars are. So you can imagine those blue dots are where all the current cars are. And it can take a query of some pickup point, for example, that green pin and some radius around it. And it should be able to quickly find like available cars and other things for you. So that's one of the kinds of systems we'll need just to offer the simple dispatching flow that you're very used to from using Uber. Cool. So, okay, now you're dispatched. Let's kind of keep going on from the trip from there. So next, you probably get matched with someone. Someone comes to start picking you up, and this is when the trip starts really beginning properly, right? So at this point, it becomes very important for us to start tracking what we call the route trip points. So a trip point is just a latitude and longitude, and like when it happened and where it happened, right? So as the car comes all the way to you, we'll track all those points. It'll come pick you up and then take you to your destination, and we'll track all those points, right? And this is probably not a surprise to you if you've taken the ride, right? Because at the end, you'll see when you get to your destination and you check your email after, you'll probably see a receipt like this. It shows the path you took. It shows like how long it took. And then, like one of the other reasons we need that is ultimately we have to like charge you a fare for it. We're not giving you the ride for free. Sorry, but so we have to know like how long it took and like all the points you took because time and distance is a major element of it as well. Cool. So then, to offer this kind of service, we have to build some kind of like location time series storage system, essentially to be able to track where drivers are going and keeping track of their exact routes. So that's the other kind of system that we'll need, and I'll kind of want to tell you about in today's talk. Yeah, so with that kind of intro out of the way, this is where I'm headed for the next 20 minutes or so. I'll first start with kind of a primer on some of the terminology we use and talk about the types of locations we collect. And then I'll kind of deep dive into each of the systems I mentioned. So first location indexing and then location storage. So you're in luck, you're gonna get 2 talks in one here as well. So I'm not gonna be outdone. All right, so starting with the first one, let's talk about what types of location data we collect. So we've already mentioned this, right? So the main thing, partners we collect data from are drivers and riders. So they both have essentially phones on them, and the GPS sensors on those phones are sending us like location updates. And as I said, location point, you can just think of it as latitude and longitude. And there's some more details, but at a high level, that'll be good enough. And then in this talk, I'll mostly focus on the driver locations because that's some of the some of the data we need to ingest to really make the systems I've talked about so far come to life. So then let me make one more clarification. I've so far kind of mentioned locations kind of as a general concept, but I'll kind of make the distinction in my talk between just a simple location point, which is just where a car might be in a certain point. So that's just one latitude and longitude, and also what I'm calling a location time series. So like where like some entity like a car is traveling over time. So this is just a set of location points over time, at some point at t equals 0, and some other point at t equals 1, etc. Cool. So that's some terminology out of the way. And then I want to introduce one more terminology about what I mean by time series. So far I've kind of drawn you a picture that looks like this. And it's very idealized, you know, like the car just goes up the road and turns right. Unfortunately, the real world isn't quite like that. The real sensor data that we're actually seeing in our systems looks something more like the picture on the top left. So all the blue cars might be all the actual GPS signals we get. And you'll notice that they're a bit noisy, and sometimes you don't have all of them. Like if the car might be having a poor, the phone in the car having a poor network signal, we're just not, you know, might not be getting those data points in the back end. Sometimes we get more than a few clustered together, and they're not always on a road because the GPS signal itself has no concept of road. So in our systems, we'll have to kind of transform the top picture into something on the right, and like this kind of transformation is just what we call map matching at Uber. I think, or not just at Uber, sorry, it's a general concept, but in short, map matching is just a way to transform that raw input into one that's fitting on a map. And we'll talk more about this in much more detail in later talks in today's presentation series, but we'll touch on this briefly today as well. Cool, so just quick recap, this is where we're headed. We're gonna talk first about the car location indexing system, something like the picture on the left, and then also a time series storage system, kind of like the picture on the right. Cool. All right, let's dive into the location indexing part. So yeah, so let's start by first talking about, you know, what we need to build such a system. So one of the first things that's kind of obvious is we need this system to store or like know about all the location points, but specifically the current location points for all the cars in our system. So that's one thing we definitely need. Next, we need these queries to be fast. So there's queries by location, and they have to be fast because we're hitting the system every time you open the app. We're hitting the system every time you hit the button to dispatch. So if these queries are slow, your entire trip experience is degraded. So we can't have that. So this has to be fast. Third, I'm mostly focusing on location, but I wanted to point out we do have to be able to filter by other properties of the car. So properties like how many people are currently in the car, like where the car might be going, and what the status of the the driver is. And like one example of why that's important is if you're dispatching an Uber pool trip, you need to know how many seats are open in the car because you can't put 2 people in a car that only has 1 seat open. So things like that, we have to be able to filter by criteria like that as well. And then, so the next thing also is the system will have to handle both a high volume of read traffic and a high volume of write traffic. The reads are coming from all of you looking at the app, so that's already high traffic. And the writes are coming from all the driver partners moving around our cities, and they're sending us location updates every few seconds, so that's also a high stream of data coming to our system. So these are the basic requirements, but one additional thing is none of this requires us to actually store this data long-term or durably, because we just all this data is highly ephemeral. It's highly it's very high time sensitive, right? We just need the most recent data. So all of these requirements put together suggest that we should build some kind of in-memory search index. So that's what I'm going to describe next. The in-memory search index that we built at Uber is called Geobase, and at a 50,000-foot view, conceptually, this is what it looks like. So it handles both write and read traffic. The writes are coming from the driver app. I've obviously elided a lot of boxes here, but this conceptually a lot of other boxes in between. But the driver app, as it's moving around, sending location updates, is coming into Geobase. So that's the right side. The read side, similarly, a lot of boxes missing in the middle, but the writer app will be sending queries either when it's looking at when you're looking at the phone or actually dispatching. So those are where the reads are coming from. So that's what the system has to do. And so the system, so you might, I think it won't be a surprise to you, it's a distributed system, but I'll first start by describing what a single node or single worker in that system will do. So let's start with what a single Geobase worker might do. So conceptually, you can think of it as storing some set of driver objects in memory. The exact format doesn't matter, but you can kind of think of it as an array. And so let's say this worker is storing all these driver objects, and it's handling these 2 types of operations, right? So first, it'll handle some kind of update operation, and I've kind of made up some kind of a schema here is not the exact schema, so don't try issuing this request against any data center; it won't work. But like so, like you can imagine that this update will update a particular driver ID, and it'll say like this driver is now at location minus 3712 12253, and it has some properties about that driver. Maybe it's on trip. Maybe it has three people in the car right now, et cetera. Other properties that might be relevant. So that's the update path. And then the query path is kind of coming in, considering all the entities on this worker. It might be based on some center location, and might be like some radius around it. So maybe it's a 500-meter radius around a certain location. And then it might also have other filters. It might say like, I only want cars that are on trip and have two people available, right? And then you might notice I snuck in like this key concept here, like a sharding key, and I'll kind of touch that next, right? So this query will have to have some notion of like how our data set is sharded, because we're not going to store all of this data on one host. So that's how a single host will work. But let me now move on and talk about how we actually shard this kind of data set across multiple hosts. So a little bit of preamble of how we do that. We have a library called Ringpop that we built at Uber. It's essentially a distributed coordination library that allows us to, like, let's say, a set of workers to cooperate between them. So for example, if you have 10 workers and they're all using Ringpop, they will all like gossip messages between each other and be aware of each other's existence. And then each worker will be responsible for like some part of your application, or some part of the index. That's a very like quick overview of it. I'm not going to go into the details of it because it's actually a very interesting topic in its own right. I'll refer you to our excellent GitHub open source page. It's you can check out all the details of it, and I'm happy to talk to you more about it offline. But like today, the interesting thing I want to talk to you about is how we use Ringpop in Geobase. So I guess we'll talk about how we actually shard the data, right? Like that's what Ringpop allows us to do. So let's talk about a few different strategies we tried. One of the first ones you might consider, city sharding, right? That's probably something that occurs to you pretty naturally because Uber is a highly distributed product. Like if I'm in San Francisco, I'm not probably requesting a ride from New York unless something changes. But yeah, so you can imagine like a worker on the left might handle all the drivers for San Francisco, and a worker on the right might handle New York. So it's a very straightforward sharding strategy. And in fact, in the early days of Uber, we did something exactly like this, and it worked reasonably well until we kind of grew more. So another sharding strategy we can try, and we also did try, is some form of geosharding. And by geosharding, I just mean take a map of a city and split it up into smaller pieces, right? So I've just drawn arbitrary polygons here, like maybe the polygon on the left has a few cars in it, and that would be hosted on one node, and the polygon B on the right has a few more cars, and that would be hosted on another node. This is another fine way of sharding things. In fact, previous versions of our system did this. But the version I want to talk to you today about is actually kind of in between in complexity, which we call product sharding. Product sharding is just exploits the natural part of like the Uber domain, where we just split by the product. By product, I mean like UberX versus Uber Pool or something like that. So you can imagine the drivers for San Francisco UberX might be on one host, and San Francisco Uber Pool might be another, et cetera, for New York, LA, or any other. It's split by product. And so just to reiterate, like the reason we did this is because products already give us the geographic separation. They're very highly domain specific to our application, so they work well. And then the other thing is, you might be wondering how we actually do the finding nearest cars and distance based. And like since they're already geographically like connected, the cars, we can just do all of our queries like doing simple Haversine distance filters. So by taking the latitude and longitudes of your driver location in your query. Cool. So I know I talked a lot. Let me kind of bring you back to like the overall architecture. So given this sharding strategy, what we have is each worker will handle a different primary key of our index. So one of the workers will handle each of the products. So that's how that works. And then, so I think now I'd like to tell you a little bit about like some of the like scaling challenges we ran into of like using this architecture. So to do that, I'll just introduce a little bit of brief terminology that we use. Just conceptually, we think of our indexes as having a size and some volume of traffic coming in. So the size is just how many cars are in it. Let's call that K, and the volume of traffic is just Q, or the QPS. And just for intuition, you can think of this as the size varies by how many people, how many drivers are on our system, and then the Q varies with how many people are trying to request rides at any given time. And as you can imagine, both dimensions vary greatly, and they vary from time to time. So like the problems that they kind of gave us, I'll kind of show on this slide, is what we call hotspots. So Hotspots just mean that one of the workers has a lot more work to do than the other, right? So like what happens when one worker has a lot more work to do becomes like the bottleneck or the weakest link in our system. So, and the reason this happens, it happens all the time, and it's never the same worker because because of the time varying dynamic nature of our system, like when there are more drivers in a certain area, that worker might just have more work to do, or if there's more people requesting. And these dimensions are slightly independent of each other and they vary a lot. So yeah, so that was causing problems for us. So I guess the techniques we used to solve that is like we just kind of tried to break up our large indexes into smaller pieces. So that's the first thing we did. So conceptually, you go back to like the index, we just, one thing you can do is just split it into like smaller pieces. So 3 pieces in this case. Another thing we can do is we actually also can replicate our index across multiple hosts. So essentially double writing, and then the traffic, read traffic to those hosts can be split into across multiple hosts. And in fact, like sometimes we do both. So sometimes we'll have like 3 partitions of a given index and we'll replicate it. So tying this all back together again, when you put it back on what the ring architecture of the system looks like, instead of just having one index handled just by one worker, we can split it across like potentially 6 workers. Like the exact assignments here are kind of technical. Like I just kind of main point is you can give exact coordinates to all of your indexes. So like a partition can be the first replica and the second part of that index, and you can distribute them across all of your rings. So that's something we've done. And that's just an example of how it might look in production. Cool. So one question that might be in your mind is, this is all well and good, but I said it was like time varying. So how do I actually like do this configuration, right? So I'm glad you thought about that. If you didn't, I'm telling you to think about it. So we basically also built kind of an auto repartitioning system. So we have an external agent called the controller, which is periodically kind of monitoring the state of all of Geobase's like shard assignments. Like Geobase is publishing those stats on the K and Q into some kind of stats database, and the controller is checking them and then reassigning them whenever necessary. So that's I can't tell you how much that's helped us. Like we don't have to worry about the system as much anymore. Like whenever there's New Year's Eve spikes or any other kind of demand spikes or other unforeseen events, the controller will just kind of take care of it for us. So that's another thing we kind of built to support that. Cool. Yeah, so I think we're done with that. So I know it's a lot of information. We can take a brief breather, and then we'll get the second part of the talk now. Cool. So that was location indexing. Let me now tell you about how we do storage. So just to remind you, storage is the feature we need to power kind of the rest of the trip features, like where you went and like keep track of all that. So some of the, it has some similar requirements to the previous system, but a few different ones. So one similar one is it also has to handle a high volume of writes, because it's also all the location updates, has to stream all that. But the key difference is it has to store these durably. Like we want the history here. We don't want just the recent things, so we can't lose these. So we need durable storage. And we also need to support a few types of query patterns. So the first one is just like a basic time series read. So you can say like, where was a driver between time A and time B? And we want to be able to answer those queries quickly. And finally, like the data, for it to be useful to the rest of the products you all use, like they have to fit on a map. Like we can't just give you like raw GPS locations and call it a day. We want it to be, this is where the driver went, this is what path it took. So we have to be able to do that as well. So yeah, let's go right into it. So let's see how that works. So again, let's start at the 50,000-foot view. Conceptually, we have a system called Location Store. It's an unimaginative name, but it gets the job done. It's what it does, it stores locations. So again, it comes in from the app, rider app or driver app. They're sending the stream of raw locations. The exact path here doesn't matter. You can just imagine there's a bunch of boxes in between as well. So what do we do with those locations, right? So first we kind of persist them in Cassandra. That's our solution for achieving the durability we need. So the raw locations just get split up by the different types of entities we're tracking, and they each get stored in Cassandra. Now, let me go one step deeper into how the Cassandra layer works. I'm not going to give you a tech talk on Cassandra. That's its own complicated topic. I'll just give you a quick 30-second or 1-minute primer on some of the details we use for it. Internally in Cassandra, you can also think of it as similar to our Ringpop application. It's just a distributed database of multiple nodes, and we have to somehow partition our data across all those nodes. So the interesting part here is how we partition the data. So in this case, like we pick a pretty standard partition. We partition by the driver ID and some time bucket. So that determines which host the data will live on, and then within that, all the writes will get stored in the same partition ordered by the timestamp. And the reason like this is kind of important is anytime you're using a system like Cassandra, you don't want you don't want to have your request have to hit too many nodes. So if you pick your partition like well, then you'll kind of have fewer like tablets to read in your read request. Cool. So that, that's how the schema works. I want to tell you a little bit more about how we do writes in the system, because one of the key requirements of this system is, kind of never goes down and has to have like really high availability. Because imagine if it does go down, you don't have your trip data, like Uber isn't, like fares don't get calculated, and none of these things work. So like our strategy is to just have multiple data centers. So we'll have a Cassandra cluster in each one. And the write replication that happens in Cassandra just gets forwarded from one data center to the next. So you can imagine that there's a red node in each cluster, which gets a request and kind of internally replicates it in that cluster. And one of them will forward it to the other one and kind of do the same thing on that cluster. So we definitely take heavy advantage of that. So that's the write path. So far, I haven't told you about the read path. So let me talk about that. So Cassandra, as you might know, is like heavily optimized for writes. I mean, it can do reads, but we prefer to have most of our like write traffic go through it. But we also have a heavy volume of reads. So what we've added is we've added a layer of Redis on top of Cassandra to kind of shed most of the read volume from Cassandra. And the reason we can do this is because the bulk of the reads we'll get is usually for the most recent trip location. So usually for the last few minutes, and we have that all cached in Redis, so that we can optimize the Cassandra layer for writes and we can optimize the Redis layer for reads. And so that's definitely served us well as well. Cool. So if you're following along at home, so far we have a system that stores the raw locations, but it's still not map matched or map fitted. So let's talk about how we do that. So I'll talk briefly about it. So I'll kind of introduce this black box called map matching. Sorry, I won't show you what's in it because that's a future talk. I don't want to unwrap the present too quickly. But the brief summary is that we have to buffer up enough data points to kind of build up context to do map matching. And the intuition behind that is it's hard to just given one point know exactly which where it fits. But if you have some context, you have a better idea of where the car is going and what road it's on. So we buffer up those points in Redis as well, and then we periodically call map matching. And then we'll persist all those data in a separate schema and location store, have the same cache, and et cetera. Cool. Yeah. So I think that's the location storage side. So I know covered a lot of material. So let me just recap. We covered how we do location. Kind of location indexing system using designed our own in-memory search index. We talked about the challenges there, and then we also described how we do our time series storage system, or what we call location store, and how we built that using like off-the-shelf technology like Cassandra and Redis, but also adapting it to our needs.